Let's now consider the rate of an enzyme catalyzed reaction. Now, what really is rate when you're talking about rate of an enzyme catalyzed reaction? So when you're talking about the rate of a enzyme catalyzed reaction, we're just talking about the speed or the velocity of that reaction. Okay, so this is just how fast you are forming products. All right, that is the rate of enzyme catalyzed reaction. So we can define it as the amount of substrate disappearing or amount of product appearing per unit time. So just amount of substrate. Remember, when you have got a substrate, substrates are going to be converted to products. For example, if I started with this, when I get to bring an enzyme to act on this one, okay, it's going to be broken. And what you are going to have at the end is you are not going to have this compound. You are going to have another thing. For example, you are going to have this piece and also this piece, meaning that you now have the product. So how fast are these substrates disappearing into products, or how fast are the products being formed? That is what we refer to as the rate of an enzyme catalyzed reaction. Now we need to know that there are a lot of factors that gets to affect the rate of an enzyme catalyzed reaction, and so when we are studying one factor, we need to take other factors constant for us to be able to determine well. All right, so now let's look at first the effect of temperature on the rate of an enzyme catalyzed reaction. So what is the effect of temperature on the rate of an enzyme catalyzed reaction? Now we need to know that the rate of an enzyme catalyzed reaction is going to increase with increase in temperature. Let me get to show how this is going to be. So on the y-axis we are going to have temperature, and then on the x-axis we are going to, let me say on the y-axis we are going to have, yes, the rate of the reaction. Okay, this is how fast the reaction is moving, and then on the x-axis, that is where we are going to put temperature. Okay, and we know temperature can be measured in degrees Celsius or also in kelvins. So for an enzyme catalyzed reaction, when the temperature is 0, it means that the enzymes are inactive. Okay, the enzymes are inactive. Remember, enzymes are proteins. So at low temperature, they are inactive. So as the temperature increases, the reaction becomes more faster and more faster and more faster until you reach a certain point when the reaction is moving at its maximum speed, and then the rate, when you increase temperature all the more, the rate of the reaction is decreasing and decreasing and decreasing until again the enzyme is going to be denatured. Okay, so at the end here the enzyme is going to be denatured. That is why the rate is slowing, but here the rate is slow because the enzyme is inactive. So as you increase temperature, you're activating the enzymes, and the reaction is becoming much faster. So this temperature where the rate of the chemical reaction is maximum, this is called the optimum temperature. Different enzymes, of course, have got different optimum temperatures. We need to get to know that. And so you need to know also the temperature that you have to supply to them. So when you are considering the effect of temperature on the rate of an enzyme catalyzed reaction, then you are going to take other factors to be constant, right? That you are going to take other factors to be constant. So specifically or basically what you are saying is that as you get to increase the temperature, the rate of the reaction increases. But when you exceed the optimum temperature, what happens to the rate? The rate of the reaction starts to decrease. And why is the rate of the reaction starting to slow down? That is because the enzymes are being denatured, they are being destroyed. Remember, enzymes are proteins at their tertiary level. So the tertiary structure of a protein, meaning there are hydrogen bonds, disulfide bonds, there are all these hydrophobic interactions. So as you get to increase more and more the temperature, you're going to be breaking those bonds. That is what gets to denature the enzymes. Alright, so the optimum temperature of an enzyme depends on the organism For example, human enzymes have got their optimum temperature mostly around 37 degrees Celsius. So while enzymes of bacterial living bacteria which are living in hot water springs, they can have an optimum temperature of up to 100 degrees. So meaning that at 100 degrees Celsius, that's where they're able to work well. So this can be some bacterial enzymes. Alright, so this is the effect of temperature on the rate of an enzyme catalyzed reaction. So another factor that we need to consider is potential hydrogen, pH. Now, just like we have seen for the temperature, also there are some enzymes which work well at a certain pH, such that when you get to change the pH, other enzymes are going to be destroyed. Okay, so here still we have got the rate of the reaction, and then here we have got the pH. So you see that some enzymes work well at neutral pH, others work well in acidic pH, others work well in basic pH. So when you have got, let's say, a reaction like this, and here you have got maybe, let's say, 7. This means that this enzyme works well at a neutral pH, neutral pH. So every enzyme functions most efficiently over a narrow pH range. So for example, an enzyme that works well at neutral pH might work well maybe from, let's say, 6.9, that is a bit acidic, to also maybe let's say 7.1. So this is a narrow pH. A bit basic and a bit acidic, they can still work. Okay, but when you get to change very much the pH, that means that those enzymes are not going to be able to work. So the pH at which they work well, that is going to be called the optimum pH, or the maximum pH. So if the pH is changed below or above the optimum, the enzyme will become denatured. So whenever you increase or reduce, the enzyme is going to be denatured. Now for temperature, the enzyme gets denatured when you increase the temperature. Okay? But when the temperature is low, the enzyme is just inactive. But for pH, when you increase or reduce away from the optimum, the enzyme is going to be denatured, and the rate of the enzyme catalyzed reaction is going to now decrease. So changes in pH leads to changes in the ionic charge of the acidic and basic arar groups. What we mean is that, remember, enzymes are what? They are proteins, and proteins are made up of amino acids. And an amino acid has got a carbon on the middle bonded to this carbon, which has got a carboxylic acid functional group, and then here it has got OH, and then it has got an amine group this side, and then you have got an hydrogen, and then you have got an arar group here. Okay, so this is an amino acid. So we are saying that changes in pH are going to lead to changes in the ionic charge of the acidic or basic arar group. So this acidic or basic arar group, when you get to change the pH, is going to be affected. Let's say, for example, the arar group which you have here is NH2, meaning that this amino acid is what? Is basic, right? Because this is the characteristic of a base, meaning that also this protein or this enzyme works well in what? In basic pH. Now if you say you change it into acidic pH, it means that this is going to be tampered with, and because of that, the enzyme is not going to be able to work well. All right, so these changes are going to lead to change in the globular shape of the enzyme, and because of that, they are going to disrupt the active site. When you get to change, because you have changed the way the arar group is, so when you get to change that, the globular shape of the enzyme, maybe instead of it having such a shape like this one, you change it, it has now a different shape. And you know that for enzymes, whenever you change the shape, then you've denatured it. So it changes from here to there, then you have denatured the enzyme. So that is the effect of pH on the rate of an enzyme catalyzed reaction. Right. So the other thing that we need to consider is the effect of substrate concentration. So substrate is just what the enzyme is going to be acting on. That's a substrate. So what is the effect of substrate concentration on the rate of the enzyme catalyzed reaction? So instead of us having pH, okay, substrate here, and also on here, instead of having pH, we are going to put substrate. So for substrate concentration, what we are going to see is that as you get to increase, remember, let's say in this reaction you have got 20 enzymes. Okay, you have got 20 enzymes. So meaning that as you get to increase the number of substrates, the reaction is going to be coming faster and faster and faster and faster and faster. But when you reach a certain point, you reach 20 substrates, meaning that all the enzymes have been filled up. You don't have free enzymes. So what is going to happen is that the reaction will stop increasing. It will just be like that. The rate will just be at the same level. Why? Because you are increasing the number of substrates, but the enzymes are few. So meaning that you will not have anything. So at this point, this is what we are going to have as the maximum velocity or the maximum rate of the reaction. Okay, so that is what gets to happen. So a point is reached, that is V max, which I've written there, when any further increase in substrate concentration will not produce any significant change in the rate of the reaction. This is so because high substrate concentration, the active site of the enzyme molecules at a given moment are saturated or they are completely filled up. So all the active site of the enzymes are completely filled up. So even when you add more substrates, that will do no change. So that's any extra substrate has to wait until a substrate enzyme complex has disassociated. Okay, so the enzyme, since all the enzymes have been taken up, so this extra substrates have to wait until they find a free enzyme. And for an enzyme to be free, it means that it has to have broken already the substrates. So this is what gets to happen. Alright. So now how can you deal with this one if you want to continue increasing the rate of the reaction? Well, you are going to increase the number of enzymes if you want to increase this rate, because you have got more substrates but you've got less enzymes. So you have to increase the number of enzymes if you want to increase the rate. Alright, so that is the effect of substrate concentration. Another thing that we can talk about is the effect of enzyme concentration. So this side we are also going to have enzyme. So this is enzyme concentration now. So we are going to have enzymes here. So it is the same way now. Here you already have substrates. All right, let's say we have got 40 substrates. Now as you get to increase the number of enzymes, the reaction is increasing also. But you reach a point when you have added also 40 enzymes, and then the substrates have all been filled up. So what is going to happen is that even when you have got extra enzymes, you don't have the substrate which are going to fit into the enzymes. Why? Let's say you have got 45 enzymes, you only have 40 substrates. Where are the 5 enzymes going to act on? So there's nowhere. So the reaction will still remain on the same level. Okay, so how can you deal with this? You need to increase the amount of substrate because you have got extra enzymes. So you need to increase the amount of substrate for this reaction to continue increasing, or for the rate to go on increasing. So this is what gets to happen. Okay, that is what gets to happen. So now if this reaction, if you have got excess substrate, okay, when you have got excess substrate and then you are increasing the number of enzymes, you are going to see that the rate will just be straight. It will just be a straight line like that. Why? Because the substrates are a lot, and as you get to increase the enzyme, it means that the enzyme will have one substrate to pick on always. But when the substrates are limiting, it means that when you've reached a certain number of enzymes which takes up all the substrates, then the reaction will stop increasing anymore. All right. So that is about the effect of enzyme catalyzed reactions. So these are some things that gets to affect the rate of an enzyme catalyzed reaction. Now let's also understand another concept, that is of inhibition. Now to inhibit is more just to prevent something from happening. So a number of substances can reduce the rate of an enzyme catalyzed reaction. So these substances are called inhibitors. So inhibitors are there to reduce the rate of an enzyme catalyzed reaction. So if enzymes are increasing the rate, inhibitors are there to slow the rate. So enzyme inhibitors can be reversible or irreversible. So reversible inhibitors can be easily removed from the enzyme under certain conditions, and the inhibition may be competitive or non-competitive. So what basically we are saying is that these inhibitors, they can either be reversible or non-reversible. Okay, so they can be reversible or non-reversible. Now these ones which are able to reverse, these can easily be removed, so you can easily remove them from the enzyme. But that means that the non-reversible ones cannot be removed from the enzymes. Once they attach to the enzymes have been stuck like that. You cannot remove them. Now these inhibitors which are reversible or which you are able to remove, they can be either competitive or non-competitive. Now what's the difference between these two? Well, competitive reversible inhibitors, in this case, so let's say this is the enzyme here. We know this is the active site. Okay, that's the active site. So for competitive reversible inhibitors, a substance with a structure which is similar to that of a normal substrate, that is the inhibitor. So the inhibitor has got the shape which is just the same as that of the substrate that is supposed to fit in the active site. Okay, so this one gets to bind to the active site such that when the substrate itself comes, the substrate will no longer be able to take in, the enzyme will no longer be able to take in the substrate. Why? Because the active site has been filled by this inhibitor, which was pretending as though it was, what? As though it was a substrate. So while at the active site, the inhibitor prevents the normal substrate from binding. Since the inhibitor and substrate compete for the active site, this kind of inhibition is now called the active site directed inhibition. Okay, active site directed inhibition, or competitive because they are competing for the active site. So this inhibition can be reversed when the concentration of the normal substrate is increased in relation to the concentration of the inhibitor. Remember, let's say you have got uh, let's say 5 inhibitors which are competing for this same active site with substrates. So if you want these inhibitors to have little effect on this rate of reaction, then use a more number or a higher number of substrates. For example, use 50 substrates. So this is going to increase the probability of substrates attaching. You know that it is all about chance. So the more the number, the higher the chances. So that is how you get to reduce the competitive inhibition. So we also have the non-competitive reversible inhibition. So this is also called non-active site directed inhibition. So the structure of the non-competitive inhibitor is different from that of the substrate. It's not the same like here where the inhibitor is the same as the substrate. Here they are different. Okay, for the non-competitive. Now what happens then? Since the inhibitor is different from from the substrate, the normal substrate. So the inhibitors in this case is going to come and attach to the allosteric site. So you might have the allosteric site here. So when this inhibitor binds to the allosteric site, what you are going to see is that the shape of the active site is going to be changed slightly. So you might see something like that. It gets to change. Okay, the shape changes. So the effect of that is that when the shape has changed, the normal substrate will no longer be able to fit into the active site. So because of that, the enzymes is not able to carry out its normal function. Okay, so this inhibitor is not going to allow the enzyme to carry out its normal function. So when the inhibitor binds to the enzyme, an enzyme inhibitor complex which is formed changes the normal globular structure of the enzyme, as we've said. When that globular shape is changed, the structure of the active site also gets to change. Even the normal substrate binding to even if the normal substrate gets to bind to the modified active site of the enzyme, the catalysis does not take place and the substrate is not converted into products. In case even when this substrate was able to manage to fit in here, because the globular shape of this enzyme has changed. In other words, it's more the enzyme has been denatured. So the substrate will no longer be able to change. Okay. So when the concentration of the substrate is increased in relation to the inhibition can be reversed when you get to increase more the concentration of the substrate. Alright, so this is inhibition. Now there are a lot of different enzymes that we need to also get to know. At least we have got pectinases. Now pectinases, they just get to break down pectin. These work on pectin. Pectin is simply a polysaccharide which is found in plant cell walls. Okay. We also have proteases. So proteases, these are enzymes that break down proteins and polypeptides into amino acids. So these are also other enzymes that we're able to see. There are a lot. Amylases, all those which get to break down other carbohydrates. Okay, so this is it for this video. Thank you so much for watching. Stay blessed.